So it's been a while, I guess. So let me quickly review the things, and then we start a little bit, and then okay, so let's quickly review what we have done. So I guess we have been in the hypothesis testing for so long, so I don't think I need to review what is the hypothesis testing, what is null, what's alternative, what's p-value, what's critical value, how to reject those. But instead, I would just straight ahead go to 2 samples. And so I guess there are basically 5 tests. I actually missed one thing here. I think I have compare proportion. So actually there's a 5 tests we will learn. And I think we covered the first 3. We just have 2 more today. And then the rest of time we will be doing Excel and R. Okay. So let's quickly review what are the tests here. So the first one is the first 2 is basically talking about looking at the means. Okay, they have the same mean. Okay, and you have 2 populations. Okay, that means that usually you have 2 categories of thing you want to compare, right? The question is, if you want to compare more than 2 categories, then it's not a big deal, right? Because you can keep doing the same thing, right? So you can suppose you have 3 different type of vaccines. You want to see whether the 3 of them have different antibodies, right? Of course, you can use ANOVA that we'll learn later this week or next week, or you can keep doing the t-test again, right? Then you can see whether the 3 are different. And there are 2 different variation, right? One is you can assume they have the same variance. The other is you can't. Okay, and of course, if you assume them same or equal variance, and how you can assume that, we will talk about that at the very end. You can do F test first, right? And the other way around is to look at the data, right? Look at the sample variance. Are they actually very similar, right? If the data shows very similar, actually it's very safe to use it. Okay, and if not, then you have to be more conservative, use more general case where you assume they have equal variance. Okay, and these are 2 independent population. And the last thing we cover, if they pair. Okay, if they're pair, look at the difference, right? The difference will just basically 1 sample, right? Because the difference between the 2 things, before and after the same subject, the pair, so basically the same identity of stuff. Okay, so they are closely related, so you take a difference, right? So example is pair population, right? It can be the same individual before the treatment, after treatment, right? Or you say, for example, look at, say, vaccine case, right? Before you have the vaccine, okay, what is the antibody level? And after taking the vaccine, what's the antibody level, right? So you can do that. And pair doesn't have to be the same guy, can be pair in the sense that you think that is important, right? So maybe look at, for example, look at a couple, okay? Look at, say, how much the money a guy make, right? And how much money his partner making, right? Maybe the wage difference between 2 couple, right? Husband and wife, then can also be a paired population. Don't have to be the same guy, okay? As long as you believe that the pair is the difference would make sense, okay? Then you can use that idea, okay? So let's very quickly go over again the example, right? So I didn't put a realistic example here, but you can imagine that just, as I said, you look at maybe the 2 different population. Maybe you imagine that the wage the income of graduate from CHK and income from, say, Hong Kong UST, for example, right? And you can see whether they make salary or they make the same one, okay? And you may consider the CHK and UST can be independent sample, okay? Maybe you can do that, okay? And remember when you have assumed the same variance and the denominator, okay, you can make it easier, right? Because you can estimate the population variance using the average, weighted average of variance, right? Because the same variance, the two sample variance are good estimate of the population variance, and you try to average them to get a better estimate. So this is unbiased estimate. This is also unbiased estimate, and you combine the two unbiased estimate, okay, in that following sense. Actually, this one, the last one, SP square, okay, is more efficient than the other two, okay? You can show that this is good and this is good, but this is better to estimate sigma square, right? Because underlying, you assume they have the same variance, right? You assume they have equal variance, right? So basically talking about X, underlying population, the population 1 have the variance sigma, population 2 also have variance sigma, right? So that's assumption. Is that clear? Is that clear? Population 1, right? And this is the interval estimator, okay? And when you have unequal variance, okay, you have two things, right? You have population 1 have mean mu1, sigma 1 square, right? And population 2 have mean mu2 and variance with sigma 2 square, okay? So that's why you cannot combine, okay? Right? Because it's independent, right? The difference between the two will be the sum of their variance, and then you replace the sample one with the population one, then you have T, okay? So that is the idea behind these equations. And what is degree of freedom, okay? It's very difficult to check, and there are many ways to calculate the V, okay? And look at the textbook and other book, they will tell you this is the right formula, okay? Looks highly complicated, okay? But this one, actually, you look at the formula, okay? This one would not be too much different from N1 plus N2 minus 2, okay? Will not be too much different from that. Okay, usually, as you can see the example, right? In the case here, okay, this is right, and if you have the case is N1 plus N2 minus 2, right? It's 88. Okay, so it's not too much different from that. Okay, unless the variance are different a lot, otherwise it will not be too different from that. Okay, so that would be the idea for this. Is there any question before we continue? Because this is exactly what we are, basically the same procedure we keep doing and doing and doing again. Okay, for the rest of the semester, basically 3 more weeks, we are doing the similar thing but different model. Basically, we are estimating the model and try to see the model with the coefficient meaning anything, do a t-test, and later we do that some f-test. Okay. So the question. Okay. And just to continue a little bit, Okay, last time we talked about this. This is the data. You may have a bunch of observations. And after we have observation, right? As I told you, when you have this, it's the same, maybe the same guy before the treatment, after the treatment, right? Or in the same family, this is the earning of the husband, this earning of the wife, okay? Or you can imagine that this is the wealth of his parents and wealth of the kids, okay? So there are many things you can imagine as long as you think they're pair. You can match the two things, okay? Then it's called paired population. And the fact that you care about difference, right? Say you care about how much the money the parents make. Is it going to be, say, similar to the kid, right? Why you care about this? Maybe you care about the right? Or poor kid and the rich daddy, is it consistent, right? Is it going to be, there is any social mobility? That's a question. Or you can imagine that, this is sales of product one in store one, right? This is in store two, the same product, right? You took a difference. You may want to see if store one is doing better than the store two, right? So that is something you may care. Okay, so is it clear what we are measuring? This difference. Okay, so and because the difference is something you care, actually this is just only one variable, right? Because the difference is something you care, and that thing you can find the sample mean, and this is the standard one sample test, which is only one variable. Is that clear? Because the difference is also one variable. Is that clear what's going on here? Okay, just one sample test. Okay, so that's why we didn't do go to very detail, because it's the same as the one sample one. Okay, if there's no question, we talk about the very last two tests, and then we go to the R and Excel. We have more fun. Okay. The last two tests we have, the first one is the proportion difference, okay? And the next one would be the variance, okay? So there are two things. So the same, remember proportion, where it comes from proportion. Proportion is when you have binary data, okay? The data is either 1 or 0, okay? A special case of a sample mean, okay? Proportion is just the mean, okay? It's just when your data is 1 or 0, okay? And here, why we care about two proportion, right? So that is very simple idea. When we talk about, say, suppose you want to see whether vaccine is effective, right? And then what you're going to do is look at people who have vaccine and people have no vaccines, okay? What you're comparing is people who have vaccine, okay? Do they got the disease? What proportion of people? Okay, maybe after 1 month, you take the vaccine, how many people got disease, okay? And look at the other comparable group, and do the same, look at they without the vaccine, do they got the disease, okay? The two proportion there, okay? And you can imagine there are two independent proportions, right? It's not the same thing. Okay, this is one example, okay? And the other example may be you want to look at, say, in the business setting, you may want to look at, in say, I think now, I think people like Mura, right? And read the news, there are some people actually waiting in Dongchong this morning, wait for their soul there, right? And the question would be like, okay, if I have a store there, right, and invite Mura to go there to do some thing to sell the product, right? And then not everyone actually going to buy, right? They just want to watch the guy singing or whatever, right? And what are the proportion of people who are buying, right? And then there's this proportion of people who are buying, right? According to one marketing channel, right? And then you want to also do the same, maybe using other method, right? instead of having mirror, you have error, right? So you can see how the difference between the mirror and the error are doing, say, for example, right? And or you can, the other question would be, maybe you guys are very young, but when I was, maybe at the time you do, right? And is one thing is a very big contention, learning about the language of instruction, whether you should use Mandarin to teach Chinese. I don't know whether the people here, but there's a big thing to talk about whether use Mandarin to teach Chinese or use Cantonese to teach Chinese, right? And then look at proportion of people who do well in, say, exams, public exam, right? This proportion test, right? So this is a very simple, usually people use it, right? Whether you see different treatment and then you can have given them a test and see proportion of people pass the test. Okay, so that's the idea. Okay, so basically you are having two proportion, see whether the same or not. Okay, and you can easily imagine that. Okay, this would be how to test these two will be very similar to the case where you have where you have the first one, you have the t-test the same variance. Okay, you can look at this formula is no different from that one. Okay, you have 1 over n, 1 over n2. This is the estimate of the variance. Okay, this is the full variance. You look at, remember this formula. Okay, let me go back to a few slides. Look at this structure here. Remember this structure. Okay, go back to a few slides earlier. Compare with this one. This is the same thing here. Okay, this guy is the variance of the difference. Okay, so remember this. Okay, the structure is the same. Maybe maybe let's see. I can do this. Do they have the? Hate it. Maybe I can do the sniping too. Yeah, good. So this is the formula here. Let's compare these two guys. Okay, this is a good one. I like this. Okay, look at this two. Compare the two. You can see it's very similar except this guy. Okay, and then you may ask why this guy is here. I will explain soon, but you can see the same structure, right? In fact, later you will see. Okay, the reason why here is like this is because remember in the sample mean, okay, but in proportion, mean and variance are related, and this is the variance. But I will explain in the next slide. But you can see the structure, okay, the same thing, okay. So basically it's this, okay. The variance you can estimate by the ultimate proportion, okay. But let me do a whiteboard to explain because this is not too complicated. I go to the little bit math, but if you're not interested in math, it's fine, okay. But just let you know, there are two things here. Okay, so we have two populations. Population 1, okay, and population 2, okay. And population 1, because the data is either 1 or 0, okay, it's either 1 or 0, so it's a proportion data. Proportion data, you know that when the proportion sample, this is the population proportion, okay, and what is the variance? See, this is the, if the, okay, which is the mu, so the pi 1 is the mu, right? When population 1 is only binary data, 1 0 1 0 1 0, the mean called mu, right, is we refer to called pi. It's called population proportion, okay, which is same as the mu thing. And actually, right, you can have basically you have mu and variance, right? But we know that if for binary data, mu and variance are directly related, right? If this is the case, right? So this is the population proportion, right? If I know the mean, I know the variance immediately, okay? Because that is coming from the data, okay? And similarly, we have mu2, this is the variance, okay? And now, okay, we can calculate the sample counterpart, right? Within the sample, okay? If we have the sample one, we try to measure it is by this guy, sorry, the sample mean, which is maybe I use this guy, right? It's a sample mean, right? And for our case, it's just the sample proportion P, right? This is the same as just sum of all the xi over n. Same here now because x is just 0 and 1, okay? So this is the same thing, okay? And we have said how to estimate this s square, right? We said it has to be n. We can do this, right? This is what we are saying, right? This is what we said, okay? And right, so we can one here, one here, one here, right? And this is also the same, okay? This is estimation of this. Is that okay? The first one. Is that clear what's going on? Now, one other thing is, another question is, besides this estimate, right? And we want to know we want to know if we say pi 1 and pi 2 are the same. Okay? So now the question is, under the null hypothesis, actually you're saying they're the same thing. Right? Population under the null, population 1 and population 2 are the same. Okay? So how to estimate pi? How to estimate proportion pi? Okay? Then it's very simple. Okay? There's the first thing is you can still do the same. Okay? P1 and P2 are actually still a good estimate for pi. Okay? Remember what is P1? P1 is sum of x from all the 1, right? And P2 is adding all the thing from 2. Okay? Can be different size, but just to make it easier, right? Maybe different size here. Okay? You can do this to estimate. So what it is that remind you, right? Remember this is, right? Maybe look at the case where you use mirror, the other case use error, right? And you calculate how many people are buying using mirror to do the advertising, and use error to do the advertising, right? And you see how many proportion of people are doing, right? And you claim they are mirror and error have the same efficacy, right? You can either use mirror or error is fine, right? They are both unbiased estimate, right? But the thing is whether you can come up with a better estimate for this to the pi, right? Because they're both good estimate. Can you come a better one, right? But the thing is, the good thing is, because they're measuring the same thing, they come from the same population, right? It means, right? Because the mean and the variance is defined by that, right? So you can basically come up with the idea, you just add them up, right? You're just adding all the x1 and adding all the x2 over n1 plus n2. This is our better estimate. Okay? So this is why you see the formula over there. Just go back to there. That's why you have this. Okay, adding all up, adding all the observation over n of them. Okay, let me repeat the statement here. Okay, so why this is a better estimate? Okay, so go back to here. Okay, the question is, you are claiming mirror and error have the same marketing efficiency. Okay, so the first thing is look at, okay, our estimator look at how many people error can make sales. 100% of people is buying if they attend the mirror activity. Okay, got the mirror there, and then how to see how many people are buying. Okay, and the same, look at the error, you do the same thing, right? That there are two different proportions. Is that clear for this one first? Okay, and now to estimate, you have to look at the variance, right? This guy, sigma, right? Because look at this, that they're the two, they're good estimate, but you can combine the two, right? You can look at how many people actually buying from mirror, how many people actually buying from error, and then over this end is the new proportion. Okay, so that is the reason why it's the case. Okay, but maybe if you don't really follow, then maybe we look at this, look at the graph again. Okay, so look at the graph again. So what it's doing is here. So actually you learn the following, right? This sample proportion 1, okay, under central limit theorem, right? We have pi 1, okay, variance pi 1 over n 1, right? And that means this, right? This p1 has pi 1 here, right? And similarly, you have this p2, right? Also a normal, okay? And pi 2 is here, right? So this is both of them actually coming from one sample case, central limit theorem, right? There's nothing new, it's just the sample mean, right? Have normal distribution with mean as the population one, and the variance because proportion, right? The mean and variance are related in this way, right? This is we learned already, okay? So now we look at the difference, right? Remember this normal, right? Sum of the normal, difference normal are the same, okay? We can still a normal. So if we want other color, maybe. That means P1 minus P2, right? And this will be pi 1 minus pi 1 over n1 plus pi 2 1 minus pi 2 over n2, right? So if you add them up, you subtract their mean but adding their variance. Is there any question for this one first? Is that okay for this one? Is that okay? So just by central limit theorem, this is the normal distribution, right? And the difference between the two normal independent, that's the mean is the difference, sum of their variance. Okay? I think you have learned it from the previous topic. Okay? So only thing is under the null, pi 1 equal to pi 2. So this guy is 0. Okay? So under the null, this is 0. Okay? And so basically is what you left is to find an estimate for this, right? Because they have the same variance, they are the same thing, okay? So you come up with a good way to estimate their common value, right? Which is equal, right? Because you say they are the same, right? Basically you say under the H null, you're saying pi 1 equal to pi 2, right? Which is equal to some value called pi, right? So basically you want to estimate pi, okay? And one of the good things is because they come from the same population, you can combine the data together, right? Because it means that there's no difference between mirror and error. Combining two data sets, the big one, look at how many cells you can make from the join the data from mirror and error. Okay, that actually gives you the p hat estimate in the notes. Okay, that's why combine the two things. How many cells you can make to the using the mirror, using error, and how people joining a thing. Okay, so that is the equation you have there. I hope this is clear. That's why you have this, right? Because you think they have no difference, so that's why you can combine the thing, right? There's no difference between the two. So that's why this is the combined data, and this is the proportion. Is that clear what we are doing there? Why this equation? Is that okay? I hope that's okay. Okay, and now the little bit difficult part is here. Okay, there's no problem with this. Okay, and you do notice that the confidence interval estimator, you can't combine. Okay, this is exactly the same one as you can see that you have the this one. This one is the one from unequal variance. Okay, and then you ask, okay, here I have the confidence interval, okay, actually coming from the unequal variance. Okay, why that's the case? Because when you construct confidence interval, okay, you don't have the null hypothesis, the luxury of same, assuming they're the same. Okay, so that's why you have to follow the common interval that you don't have the luxury same, they're the same. So you cannot pull them together as above there. Okay, so that's why and the difference between the two equations, right? You may ask, why don't I have pi bar and p bar and p bar there? No, we cannot do it. You can do it p bar because you under the null hypothesis, they're the same. So you can combine the two data sets into big one to calculate the grand proportion that you can do it. Okay, but now you cannot do it anymore because under the confidence interval, you cannot assume they're the same. Okay, unless you think they're the same, you can do that, but it's not reasonable to make the same assumption. Is that clear what's going on there? I mean, other things are the same, but let's see an example. But I hope I make things clear. As I said, if you really can't follow, that's fine. I mean, we're not math class. We're not going to ask you to reproduce those kind of things in the exam, but I try to convince you that's the case. This is the right formula, okay? And as I said, I mean, probably you will forget it anyway, but at least I try to convince you every formula have some reason, okay? And it doesn't really matter you remember those, but just try to not just blindly remember, try to understand. It's a good learning process, okay? Because at the end of the day, this is the formula you need, okay? And you can explain why we have this equation and why we have this equation, right? Because this one, they don't have the same variance. You have to stick to the, all right? You stick to the old formula. But in the case where you know that you assume they're the same, right? They come, okay? So now we have this, okay? This is a very simple exercise. You have two population the first random sample of size 50, the sample proportion is 0.6. The other one sample size 40, the sample proportion is 0.7. So the question is, you want to see. So basically, if I use a mirror and error example, we consider I have a mirror event. I have 50 friends there. Okay. And turn out to be 60% of people actually buying the product. Okay. And I have another event. I have invite error, and 70% of people are buying the product. Okay. And then you can try to see if mirror and error are the same advertising efficacy. Okay. This is the example, right? So what you're going to do is first I calculate p hat first. Okay. And this is n1 plus n2, how many of them? Okay. And this is actually how many of them from how many people actually buying, right? From mirror, and this how many people buying from error, right? And then you combine, and then you have 58 over 90, right? So this combined data give you a how many people actually buying. Okay. And this is the formula here will be just this one, because they're the same, this is 0. Okay. So P1 minus P2. Okay. Numerator. Okay. And this is pi bar, 1 minus pi bar, right? 58, 90 minus 58 is 32. 1 over n, 1 over n2. So you get a negative r. Okay. So just to remind you what's going on here, right? Remember, we have P1 over P2, okay? Assume they're 0, okay? And we need to convert it a Z here, right? So the question is now, just to remind you what's going on here, what you get is negative 0.1, okay? And you say we're doing a two-sided test. So we're asking whether this area multiplied by 2, is it more than alpha or less than alpha? Okay. And now we convert this 0.1 into here is actually 0.98. Okay. So the first thing is to calculate area. Okay, times 2. And this is the number. Okay. And just remember how we do it in the Excel. Will be the norm as this, right? Negative 0.98 and then true. Okay, and then 2 times. Okay, this is the area. Okay, and you tell the area, I'm not going to repeat because we do this too many times, is very big. Okay, so you cannot reject. So you cannot say, in this case, if you talk about mirror and error, they don't have difference in terms of advertising ability. Okay, maybe mirror can attract more guests, but they are not converting the thing into sales. Okay, so that if you take this example, and other than that, you can look at the critical value method, right? Basically, it's actually rather simple, right? Because you don't need to do Excel, right? This, as I said, this one you know very well, 1.96, okay? And this number, right, two-sided is here, so you cannot reject. Okay? And just to remind you why this, how do you get this one? I think we have repeated too many times, but this is just the norm dot s dot inward, okay? Because symmetry, what we want is that both side is alpha over 2, okay? And the same as here, right? Okay, and alpha is 5%, so both sides is 2.5. Either you take 97.5, okay, give you the right side, or 0.025, okay, give you the left side, okay. And this is either 1.96 or negative 1.96, okay. Figure the symmetry. Okay, I don't think there's an issue here. The last one will be just remember when you have the confidence interval estimator, this is the numerator. This is a critical value. Okay, do note that this denominator is not same as this one. That they have the same thing, so you cannot just use the beta estimate. You have to separate. You have to calculate the variance for the first thing, the second one. This is just P1 1 minus P1, P2 1 minus P2. Okay, P1 is 0.6 and P2 is 0.7. Okay, so that is the main tricky part there, because you cannot assume the same. Okay, the only difficulty arises here because of the relation between mean and the variance in the proportion data. Right, when you calculate sample mean, population mean, those things, you don't have this problem. They're the same because they're separate measure, right? You have you have estimate this by sample variance, right? But now this and this are closely related. Okay, so that's why the formula is a little bit tricky. Okay, is there any question? I guess this is the last proportion thing we do. There will no more proportion for the rest of the semester. So say goodbye to proportion. No more proportion. Okay, so this is the end of proportion. For our course, we will no longer see proportion anymore. Okay, so say bye-bye to it. And of course, you will do an assignment properly. After that, then you don't have. Okay, so I guess we should have break, but before break, I think we should give you the idea for this one, because this is very simple. Okay, and I'll come after the break, we will continue. So let me introduce what's going on here. So last class we talked about the compare sample population mean. Look at the mean, they're different, and we just look at proportion. So lastly, we want to compare variance. Okay, and and we will use something we call F test. There's something we call the chi-square. We have T, and then we talk about F. Okay, so we are doing F here. Okay, so F is talking about variance. Okay, and remember F is just between two chi-square, and chi-square is measuring the variance. Okay, so basically that's why it's a good estimate. That's why you use F, because chi-square, the ratio of chi-square is F. Okay, and chi-square is talking about sample variance. Now, so when we will use this, okay, one thing to look at is why we care about whether two populations have the same variance. Okay, one thing is if the same variance, then we can use the t-test, right, to see if the mean is different or same, right? Another reason why you care about the variance is talking about say accuracy or product quality, right? Is whether the machine is stable or not, right? Imagine that your production manager, you want to make sure the two machines, right, from the same, is it going to give you the same production error, right, or same accuracy, right? Then actually you talk about variance, right? You talk about which two machines is good, all right? And an example will be probably those who are not from Hong Kong may not familiar with our subway system, right? The subway car used to be from UK, which is supposedly very stable. You don't have many problems. But recently we are using the machine from Korea, from China, which is cheaper for sure, but there are more problems. Okay, and may not be the problem with the product quality, but probably is because of the whole system, the UK system. When you have introduced system from Korea, from China, from elsewhere, or from Japan somewhere, then may not be consistent. Okay, then you may want to see, okay, is it true that actually you have more problem? Okay, look at the variance, right? So that's the idea. Maybe just due to some other mistake, right? And the other thing is variance, as we said, is a measure of risk, right? We talk about investment, right? And then the question is, two different investment portfolio, right? Hypothetically, right? And you want to see whether the investment have the same risk or not. Look at the data, right? Suppose you want to say, oh, let's invest in India, okay, or Indonesia, okay. Which market is more risky? They all are emerging market and they are going to have a good return, right? Maybe the return is similar, okay. They have the same mean, right? Maybe test that mean, right? Look at India, Indonesia, okay, maybe have same mean, okay. So the next thing to you to do is which one is more risky? Okay, you cannot distinguish that they have different return, okay? The same return or similar return, right? So the thing is, okay, which one is more risky? You want riskier one, then you use this F test, okay? Here I only saw one-sided one, okay? And probably when you do investment, you should do one-sided, right? Because you want to see whether actually that one is more risky or not, right? Because you can look at the cases one-sided and two-sided means you put more area on the end, so it's more conservative, right? You should do use one side instead of two sides, right? Because two sides you have to both area, and one side that you put area on all the one end, okay? So one side is more conservative, and probably we'll talk about after the break. But the F distribution, if you remember, I said, look at the graph is T and normal is symmetric, right? But F is no longer symmetric, okay? So that means that when you calculate the critical value, it's no longer symmetric. You have to calculate the left and right, okay? And p-value, we still use the same thing multiplied by 2, okay? But the critical value method is a little bit more difficult. You have the two different value, okay? Because before it's symmetric, around 0, but now it's the left and the right is a little bit not the same, because talk about ratio, right? This is at least is 0, right? And most can be very big, okay? So it's not, okay? And basically, the simple thing is, it's very simple. You just take the difference, take the ratio of the two sample variants, right? So basically, we want to look at, say, Indonesia and India, right? Okay. Here, I don't need to assume the same mean. They have a different mean. Doesn't really matter. We don't have to make assumption they have same mean. Okay. They can have different mean, but just compare the variance. But it will be more meaningful with the same mean. But we don't have to assume the same mean. They're different means. Fine. How to test it? You just look at the ratio of the two. Take the ratio, and this ratio is F. Okay. And then you need to. The only thing you need to check is degree of freedom. It just n1 minus 1 and n2 minus 1. Okay, just depends on. Of course, was one of two, you can flip it, and you can just flip this guy, right? So that would be the idea. After the break, we come back. We talk about the example, and basically we end all of this, and we will do the R and Excel for the rest of the class. Okay, that's a break. I answer a question you may have. So let's resume. So we come to the last hypothesis testing. Last test is testing variance. Just to remind you what we're doing. Do note that this F test, okay? This is the thing we'll be using the next topic, ANOVA. ANOVA, we'll be doing all variance. Okay. So basically, I can tell you the main idea. Main idea is there are two different type of models. Okay. And we want to compare different model, which one is better. Okay. And if one is more simple model, one's more complicated model, right? If the complicated model makes sense, right, then the variance will be smaller, sufficiently smaller. Okay, so then it will basically fitting the data better, having smaller variance. So that's why we are comparing the variance. Okay, so the idea is very simple, right? The idea is very simple, right? Just you can imagine a couple, okay, one boy and one girl, okay. Before they get married, they may be fighting each other, okay. And if the marriage is good, okay, then they fight less, right? Fighting you can consider variance, right? So you can just say if this marriage is good, then they fight less, right? So that means the compare variance. If the model is good, okay, then you have less variance. Then that's actually basically the meaning of ANOVA. Then we will talk about this next class, but let's focus on comparing variance. But we'll talk about this more detail in the next class. But the idea is saying that if the model is better fit, okay, the couple is good, they will have less fighting, right? Less quarreling, less argument, okay. But we just study the variance now. We don't talk about how to use it later. But this one will be F test. We'll be using it for the basically. If you look at the slide, you can see will be the next class, the class afterward, and then part of the regression we will use F test. Okay, because compare variance is a good idea, right? Because of whether the model is a good fit, is good, is useful, it should reduce the variance. Okay, you should reduce the variance of things you can't explain. Okay, so so that's the main idea. Okay, now let's go back to here. We have two sample. Okay, and one important thing I didn't say it here is you have to assume, okay, the underlying thing is normal. Okay, we have two population. Okay, we have to make sure that this is normal and this apply. Okay, so this is different from the idea about testing the sample mean and sample proportion. Sample mean, sample proportion, we don't need to have a normal assumption because of central limit theorem tell us the sample mean is already normal. Okay, but here we don't have this luxury. Okay, we don't talk about sample mean, sample variance. The sample variance, we don't have anything to say unless we know the underlying is normal. Then this will follow F. Okay, so we don't have we have to assume at least the underlying population is normal. Okay, just let me clarify again what's going on here. Okay, so just very quickly, I hope this can remind you what is the important assumption here. So when we have data X, okay, I don't care what it looks like. Okay, central limit tell us this have to be normal, and that's how we have all the normal Z test and T test can be based on. And because this one will be the Z test, we don't have much issue there. Okay, but and T test, okay, T test rely on this guy, okay, and when n go to big, then this one also has no problem, so that's not a big deal. But when you look at about the variance, what is this guy? What does it look like? Okay, we don't know. Okay, but if we are able to assume this is normal, okay, and this look very nice chi-square is like this or like this, depends. Okay, and you got the ratio of these two variance. Okay, this is a nice F. Okay, so you need to make some assumption on this guy. Okay, so you make assumption on the underlying X is normal, then we can have this assumption. Okay, but anyway, let's go back to here. Okay, so this is the ratio of the sample variance is normal. Okay, if the underlying distribution is normal. Okay, but anyway, we always assume this for our purpose. Okay, so that's not a big deal. Okay, it's only a big deal when you go to more advanced class. They will talk about what happened if those assumptions is not satisfied. Okay, so and to be honest, most likely when you actual practice, they just assume normal. Okay, and yeah, there's nothing you can. I mean, most of the time is this just makes that assumption. If not, then you need to rely on more complicated procedure, which is usually is not a big deal. And for business application, actually it doesn't really that matter because you usually have a large number of data. So normality is not an issue. Okay, that may be an issue when you do small sample testing. Okay, when you have very small sample, you may have little bit issue over there. But when you remember when data is large enough, then normality is usually not a big deal. Okay, so that is not a big deal. When you have 50 and 40, it's really too small for business application. And most of the time you have 500 or 5,000 data points, so that's not a big deal. Okay, so look at the question again. So we have the question is as follows. So population, this is N1, okay? This is S1 square as variance, okay? Sample size, this is N2, this is S2 square, okay? And you are trying to claim that to see whether they have coming from the population with the same variance, okay? We don't know whether the same mean or not, okay? If you want to see whether the same mean or not, you should go back to the t-test and see whether the same mean, but we only want to check the same variance. We don't make any assumption about the mean the same or not. Okay. And the test is really, really simple. You just take the ratio of the two. Okay. So basically it looks like this. This is the F looks like. Okay. F will be 49, 39. Y just N1 minus 1, N2 minus 1. So this is the F. F looks like this. Okay. And it's unlikely to be 0 Okay. And of course, whether it's skew more this way or skew the other way depends on which one is bigger. Okay, but looks like this kind of shape. For sure, it's not symmetric. Okay. Again, this is 1.5. Okay. The question will be, the idea is very simple, right? This is, remember, this is S1 square over S2 square. Okay, it's this guy. And look at the data, what you have the data. This is 0. Okay, the data is 5. Sorry for the writing, because this screen is not really easy to write. Okay, so now what we want is to ask, simple thing is whether the 5% on both sides is going to be there. So basically just, although it's asymmetry, we still do the same thing. Look at this over 2. Look at this alpha over 2 and see if they are the same or not. Okay. Or you can look at this area, calculate area to see if this is more than or less than 5% after you multiply by 2. Okay, because we're talking about two-sided test. Okay, if one-sided, then just one side. Right now, this two sides. Okay, so how do we do two-sided? Look at the area. Let's calculate the area. So suppose we want, now we want this area. Okay. So the question is, if you want to do this, the question is whether the left-hand side is bigger or right-hand side is bigger, right? Because you know before you have 0, okay? The p-value is very simple, right? Just go to the extreme and multiply by 2, right? But here you don't know which side is smaller, okay? So first you calculate whether which side is smaller and multiply by 2, okay? Actually, it's very simple because the area is more than 0.5, right? If more than 0.5 the area, you multiply by 2, then it's more than 1, right? The p-value cannot be more than 1, right? So just 1 minus it, we calculate the other side, multiply by 2. Okay? Then repeat the statement. Okay? Actually, this one, you don't know is, if you don't know the graph, you don't know whether it's here or actually you're here. Here, right? You can just, this area multiply by 2. If here, this multiply by 2, right? But if without looking at the graph, you don't know which side you're in. Okay? How do you know whether you are left-hand side or right-hand side? Calculate the area to the left first. If more than 0.5, you should use the other area. Is that clear? Why we have to do this? Because you don't know which is left or right. So the thing you do is look at whether the area to the left is more than 0.5 or less than 0.5, right? If less than 0.5, then you're done multiply by 2. You get the p-value, right? If this is more than 0.5, actually you are, or should be on the right-hand side, so subtract it, look at the tail, and times 2. Is that clear? Is that clear? Just very simple idea. Regardless of what, right? So you must be, you should be very careful. Okay. So look at this 0.5. Okay. Look at the area. How to do the Excel thing? Look at area. How to calculate the area? Right. You want the probability F is 39 is less than 1.5. Okay. So look at the Excel. Look at the Excel. This we call the F dist, right? The left-hand side area is the F dist. 1.5, 49, 39. And then put through there. Okay. Let's do that. So same as T, but you have the 2 degrees. Y is the F dist. Okay. It's 1.5, 49, 39, true. Turn out to be 0.9. What does that mean? the area to the left is 0.9. So what my graph here is wrong. Okay, it's not on this side. It's actually far right. Okay, so I should 1.5 is not here. So I should what is actually the 1.5. It actually look at this graph. Should actually be, I use other color, maybe black. Should actually be here. Okay. The left hand side, all the area is 0.9. So this area is like 0.1. Right? So basically the p-value should be subtract from it, multiply by 2, right? Should be 2 times 1 minus this guy. Okay. So the p-value would be like 19%. Is that clear how the p-value is being calculated? Okay. You just calculate the area to the left. If less than 0.5, you multiply by 2. Okay. And otherwise, actually this idea apply the same thing when you do all the two-sided tests before. Okay. Basically calculate area to the left and you less than 0.5, you multiply by 2. Otherwise, 1 minus it times 2. Okay. This procedure actually the same. But we know it's symmetric by 0. That's why you don't have to do this procedure. Because you in your mind, you already do it already. Okay. So this is the p-value of this. Okay. Now the next question is, if you don't do p-value, how to do this, right? Then you just have 2.5% on both sides, right? So you just F inward. Okay. So what's the left-hand side? Okay, left-hand side. The left-hand side will just be F inward on 0.25, right? 49, 39. Okay. And the right-hand side one, right, will be F inward 0.025, 0.975, 49, 39. Okay, the critical value are 2. Okay. Just let me repeat here. You just F inward 0.025, 39, 49, 39. Okay. And the other was F inward 49, 49. I hope this one, okay, can convince you. This is how we do it, right? This is 1.8 is here, okay, 0.5 is here. So this 1.5 is within these two critical values, so you can't reject. Okay, is the left side value is 0.1.55, the right hand side is 1.8. Okay. Is that okay? So this is nothing new, but it's not symmetric. So you have to be a little bit more careful when you talk about calculate p-value as well as you calculate the critical value in the both sides. So there's nothing deep here. Is that okay? And if there's no problem, then I think we're basically done for this set of slides. Yeah, any question? So is that okay? So the last, can I erase? Okay. The last set of slides is just saying if there's nothing you can tell 1 or 2, right? You can replace 2 and 1, right? And you reverse the order, everything the same, because this the graph is just reverse it, you should get the same result. Okay. There's nothing special about 1 and 2. Okay. So that's why when you take difference of the mean, you just this is symmetric, right? So it's the same thing here. Okay, I'm not going to repeat it, but just you replace this guy and everything just reword it. Okay, there's no difference between, there's no special about 1 and 2. Okay, if you flip it, you just flip this 2. Okay, your answer should be the same. Okay, because this is it, you can easily see that from this exercise, okay, you should able to see f n1 minus 1 n2 minus 1 should be same as this f n2 minus 1 n1 minus 1, right? You just flip it, you just inward, you just reverse. So everything is the same thing. Okay, so that's why look at the F table. You just need one F table, right? You don't need two. Okay, for degree of freedom, you just need you look at the table in the textbook or other thing. You can see I just need one table, different N1 combined different N2, because if you flip it, this one flip. Is that clear? So but I don't think that is very important idea, because we always use the computer anyway. So this is this property is not super important, but just now you know the same thing. You just flip things. Okay. I guess now is the time to do some Excel. Okay. Yes. Is there no question? So I think we have done this. There's one sample test, the Z test. Okay, we've done that. The T test, we also did it. Okay, for 2 sample 1. Okay. I think we did that, but let us go over again. Okay. So we are going to learn this T test formula. Okay. And then we learn some add-in. Okay. So just to remind you how to do the Z test very quickly. So do the Z test, one sample Z test first. Okay. Remember how we do it, just to remind you, because it seems a little bit quite a while. So to support data, we have this one, right? We have some data here, just to remind you what's this. Okay, the data, right? And we have the mean mu, okay, and we have sigma. Okay, sigma is given by you, given by someone, maybe 0.5, I don't know. Mu is like, this is the hypothesis you want to do. Okay, so the question is, you want to do a I think it's two-sided test, right? Yes. So this one gives you the right side p-value. So this is a if you want to do the one-tail test, okay, right hand side, you do the same. It's a C test, one tail. C test. Okay. One tail one will be just C test. You click this guy, okay, and this is the mean, and this is this guy. Okay, so this is exactly the right tail test for one sample. Okay, just to remind you, this is the case. We have did that last class already. So this is, remember, this is the right tail p-value. We did it last time. Okay. So for the p-value test, we don't have the formula there. Okay. Now go to the t-test. This is t-test. Okay. And this t-test is 2 sample t-test. Okay. This t-test is 2 sample t-test. And what you're doing is you and you tell them it's a one tail or two tail. This argument is. Here you have the last digit. The last digit have two things, 1, 2, and 3. Actually correspond to our notes. Okay. If 2 is equal variance, if 3 is unequal variance, if 1 is a pair. Okay. So let us show you how to do it again. I guess we have did it last time already. It's a two sample t-test. Okay. So let's do it quickly. So we have x1 and x2. Okay. This is the data. Just randomly put in data. So here we don't have to have the same number. If you're talking about independent, we talk about independent sample. Independent. Okay, independent. We don't have to have the same number. Okay, I just input some random number here. Okay. So then what we're going to do is do a t-test. Okay. We're doing a t-test under same variance. Okay. And then we will do another one, t-test of unequal variance. Okay. And then we'll do the same is the first one, we will do a right tail. And I will do the both tail. Okay. The same here. Okay. So what's the formula here? Right tail will be just t dot test. You put the data here. You highlight the data. Is that okay? And then you have to tell them the tails type. Okay. And then you tell them it's equal. Okay. If two tail will be the same idea, is t test. Again, you highlight the data, highlight data again. You tell them it's a two tail and it's unequal variance. It's equal variance. So you can see the right tail is just this one. Okay, it's one tail. I think it's not just yeah, I think this is the case. I think it's one tail rather than both tail, I guess. Anyway, okay. So you can do the same here is t-test. If unequal variance is more general, just highlight this and highlight here. Okay. And you have two tail. It's one tail first, and you have 3. Okay. This is how we calculate that. If two tail, let me copy. The two tail will be same thing, just t dot test. Okay, you just have to highlight this and highlight that, and you give two tail, and you have unequal variance. So I hope this one can convince you that it's easy from data to calculate the t-test. Okay. So before we go to the other case we call pair the sample, I want to show you that you can also do this using Excel add-in. Okay. I don't know whether you have this in your iPad, but we'll be using the data analytics. Is that okay for this two fund first? Okay. Is that okay? This one I think we covered already last time, but just in case you forget. Okay. And remember how we do things from scratch, right? I think in the last class, we also do things from scratch. So now the thing is, let's do it using the data analytics. Okay. That is actually easier. Okay. But it's just go to the data. So we don't have it now. We have the, there's nothing here. So we have to comment out, go to file. I hope you still remember how to do add in. File, option, file option, and add in. Okay, this is inactive application add in data list. You have to get it out because it's inactive. So we go to go, and it's to pack. Okay, that comes here. Is that okay for this one? Just remind you we're doing this again. Is that okay? Is that okay? Okay, if that is no problem, what we do is we just use this data analytics to take out the thing. Data analytics. We have something we call, okay, t-test equal variance, okay, which is the first one. Okay, t-test two sample assuming equal variance. And you ask you to look the range. Okay, this is the range. And here we have labels, so that's why you can go from the beginning to an end. Okay. And variable 2 will be just all the thing, right? Whole column B. And we have label, that's why we have the label there at the top. And we usually want to test is 0, so just put 0 there. And alpha is the same alpha we have in the class is significant level. So just click OK, but of course you want to put the output range because I want to put it somewhere in the, I want to put it, say, I don't know, maybe here. Okay. And I want to output it. Okay, is that okay? This variable 1 is column A, variable 2 is column B. Okay. And difference 0, label is you because you label. If you don't label, then just from 2. And alpha is just what you want to put 0.5% or 2.5% or whatever. Okay, or 1%. Okay. So this is output range as you decide. Okay. Okay. So now you can see. Let's go to this side. Okay. So you can see this number here. Same as this number. You put this green here, same as this green. Okay. So exactly, let me move this up. And using the add-in, you can see the calculate mean, variance, observation, all the thing, the pool variance, and all so on and so forth. Okay. This is the SP square in our slice. Pool the variance. Okay. And this is what you input, degree of freedom is this plus this minus 2, right? Test statistic will be this difference over square root of this guy times 1/6 plus 1/9 is there. Okay, everything is there. Okay, so this is exactly, you should know every single entry there. Okay, you should, that's no problem. You should know every single thing. You could able to calculate. Is that okay? Is that okay? So we can do unequal variance. That's not complicated, right? So we just do the same thing. Let's do it again. But instead of go to data analysis, instead of equal variance, go to unequal variance. Okay, unequal variance. And do the same. Okay. X data range is coming from all the thing X. Okay, all the way up. You include the first one because you want to include the label. And variable 2 we also do the same. Okay. and your hypothesize they have different mean, that there are different to 0. Label is not there. Output range, you can tell them, maybe I want to put on the right hand side of here. Okay. Now you can produce. Okay. And you're able to see everything there. This number, let me put it, I don't know. Yellow is same as this guy, right? And the p-value of this, the two-sided one, I don't know. Gray is same as this one. Okay. So this two value is there. Okay. And okay. And look at this mean variance, same as the thing when you have unequal variance. Everything the same. The only thing you don't have this pooled variance, right? Because you don't have this thing. Okay. And you calculate the t-stat. Okay. And then remember, when you have unequal variance, the only difficult part is the degree of freedom, which we don't show it here, but you can see this number is given from that. The critical value are based on those. Is that clear? How we can do Excel add-in? Okay. So the next thing is what we call the I think the paired. Okay. We do a two sample paired. Okay. And actually this is nothing new, right? Because it's just x1 and x2. Okay. And we have some number here. Okay. And we have some number there. I just remember it's pair. So that means that you have the same number of observation. Right? It's the same number of observation. So the first thing to do is to calculate another thing called D. And D is just x1 minus x2. Right? So what you're going to do is to have a t-test on this one. Right? You can do a t-test on this one. Okay, you can do a t-test on D, one sample t-test. I don't think I need to tell her to do it. You know how to do it. Okay, but what I want to show you is okay. You can do the t-test on this one, on the D. Okay, but what I want to show you is you can do a shortcut, right? Instead of calculating this, okay, you can do the t-test. Okay, by using the one tail and two tail here. Okay, you will use the t dot test x1, x2, one tail using pair. Okay. Okay. So that is how you do a one tail test. And two tail will be like this. So you can see they're different enough to do this. Is that clear? How you do a two sample t-test. Okay. If you are, this is technical, if you're smart enough, you can notice that that's the reason why you don't have one sample t-test in Excel is because you can create a column of one sample and a column of 0. If you do a on these two columns is same as you do a one sample t-test. Okay, if you understand, it doesn't really matter. But anyway, let's do a data analytics. Okay, to add in. Okay, and there's a two t-test paired two sample for means. Okay, so let's do that. Okay, let's do that. Variable 1 is column A. Okay, pair the sample. Column 2 is this guy. Is that okay? And hypothesis is 0. And okay, so is that okay? So I have a data from A1, data from A2, and then I have 0 and label. Output is just put random, maybe we just put here. Getting small. Maybe I just do it not here. Looks terrible. I put here. Output in the other area. Put it here is better. Okay. So in this case, you can see the answer is here. The same thing. Okay. And the answer is here. Okay. You should be able to see okay. Everything here you should know. Okay. This correlation is just a thing, the Pearson correlation is the standard thing we have in the topic 1 correlation. Okay. That's the covariance over the 2SD. Okay. And this is t-stat, the same thing. Is that okay? Is that okay here? Is that okay? So I want to show you the last thing is the F test for today. I don't think I have time to go for R, but let's do the F test first. F test. Okay. F test is you have two data sets. Okay. Again, I don't know what's the number, doesn't really matter. Okay. Make up some number here. You don't have to follow me, just make up some number here. Okay, just make up some number here. There's two columns here. I want to do an F test. Okay, and F test, you remember you don't need really worry about the sample mean and sample variance, right? So it's S2, S1 square, and S2 square. Okay, you calculate this two. How to calculate S1 square, S2 square? You just this is the formula. Okay, you calculate variance of S1, the sample 1, and the variance of sample 2. Okay, and you have the F statistics, right? Just the rates of the two. Okay, so it's very simple, right? F test. Okay, and probably you want to calculate the N1 and N2, right? N1 and N2, right? N1 just counting how many of them. And N2 we just count how many of them. Okay. Now, there are two ways to calculate. Do you remember how to calculate p-value? First, you want to calculate p-value. to look at the F list, right, of this, right, and you have x minus 1, so this minus 1 and n2 minus 1. Okay, true. So is that clear how we do? Look at this value. Look at the left-hand side, and 5. So what we're going to do? You take 1 minus this and times 2. So you have 1 minus this and times 2. Okay, so the p-value is 0.96. Okay, and this is the value you want. Okay, and now you want to also look at the case where you use the data analytics, and I should end here. Sorry for a little bit overrun. So data analyze, go to the F-test 2 sample for variance. Actually, the same procedure here, F-test 2 sample for variance. The procedure same, just variable 1 and variable 2. Okay, you have labels. You put the output range here. So this is the same as the t-test. Is that okay? The same thing. You use F for variance, and then you're done. Okay, you just tell them where to output. Then you decide where to output, then we're done. Okay. Okay, so that is how they just do one-sided p-value. This is the one tail, so just do one tail. One tail we just do. They just do one tail in the table. So I just keep the one tail here. Okay, this is the one tail. They do 1 minus. I don't know why it's not quite white. Anyway, it's not quite white here, but this is what they're doing. They look at the smaller one. Okay, so their one tail is not exactly one tail, but the Excel and the one tail just automatically pick up the smaller one. Okay, so this is rather anyway, but this is what they're doing. They multiply by 2 is this one. So this is how the Excel is doing is they pick up the two-sided p-value and divide it by 1. So this is how actually they do the one tail. Okay. This one is not really what they're actually saying. So just be careful about the one tail in the Excel. Okay, it's not actually less than that, but rather they just take the left-hand side, right-hand side, right, and just figure out that the one that is less than 0.5. Okay. So I hope we show you how to do the F-test. Okay, we show you how to do all the tests in Excel. So you're able to do it on your own. So I shouldn't take more time than I should. I'll stay around to answer any question you might have. But for the hour, we will do it when you do ANOVA next time. So don't worry about it. Shouldn't be an issue. So I answered the question in my head, but you should be happy now. You should be able to do hypothesis testing. That's no problem. And the new homework will be available. Again, you're given 10 days to do it. All right, do I have? Yes. So after this homework, there will only one more homework, and that's it. So 2 more homework for the whole semester. Okay, so you can go. I just answered any question in case you might have any. So I see you on Wednesday. Okay. Is Wednesday here? No, I guess not, right? Wednesday is in the usual usual room. Where is the usual room we have? Yeah, in the morning is down there. Yeah. Yes. So the question is the data analysis. Yes. F test is here. Oh, how to get the data analysis? Simple file, options, add in, and then go. And then you have tick here. If no tick, then tick, make sure they tick here, and OK, they appear. I think we covered this in the very first class. I mean, yeah, that's okay. But if your computer is on, then you don't have to do it every time. Because the computers, if you have done it in your computer, then you're done. You don't have to do it every time. Okay. Please only do it because you haven't done it. So you don't have to do it. If your computer is already on this one, you don't have to worry about it. Okay. So yeah, see you. If you have a question, let me know. I mean, just try to answer it for someone taking our classroom.